Woo! Hey there, and welcome to Tucker's Computer Corner, or, as my blank would say, insert punchline here. Oh, I guess I forgot to fill that in. As you might know, I've been working on an iPod Nano 3rd generation NAND mod to increase its storage capacity. I'm still working on it. I've made some breakthroughs, including validating my guesses about the FMIS instruction set, which is cool, but not what this video is about, as you can tell by the title. As you can also tell by the title, this is not part 1. There is no part 2. I did it. It worked. This is, to my knowledge, the first digitally integrated iPod Bluetooth mod. Here it is implemented on my favorite target, the iPod Nano 3rd generation, which might make this the first Bluetooth mod designed specifically for the 3rd gen Nano. But what makes this mod so unique? Well, first, it uses a completely digital audio path. It doesn't go through an ADC or a DAC, it's digital all the way to the speaker. Another cool feature of this iPod is that you can actually pick what device you want to connect to. So the iPod is off right now. I have external power going to it again just because the battery's kind of weak in this one. I'm going to go ahead and turn it on. Okay, it's going to boot up and it's going to start looking for devices to connect to. See, it's already found my OONTS angle here, so I'm going to say connect. There you go, it's connected now. And it's going to boot into the operating system. And then I'm going to come down here to shuffle songs. So I'm being very gentle with this. And there you go. And we still have control over it. Excellent. And again, the entire setup, I just have some external power running to this just because the battery's really weak. But yeah, it's a completely wireless, completely digital, with control, iPod Nano Bluetooth mod. It's made of widely available components with an easy-to-assemble board, even with passive components the size of crumbs. It uses the Arduino environment, so it's easy-ish to program, and you don't need the ESP-IDF to do so. And finally, and this is my favorite, there are no dongles. Just, incredibly complicated soldering. Everything you need is in my GitHub linked below. But how did I do this? Well, it wasn't at all easy, and before we start, let me just say, you're probably never going to do this mod. It's not easy to implement at all. I'm going to go through the roughly year-and-a-half-long journey it took to get here, along with the design iterations and debugging steps. If you want to skip to the show-offy bit and the installation process, I've marked this video with chapters that you can use. So let's talk about the design process and some of the engineering that went into this. What you're looking at here is the 4th revision of the PCB. The design for this board went from relatively simple to really complicated, and then simple again. Let's take a walk through each of these boards and relive some of my pain. Designing PCBs is relatively new to me, and I kinda sorta jumped in face first on this one. The first board was based on a simple concept. I'd find a really small Bluetooth transmitter and make it work with the iPod. I designed a board around this piece of crap, the KCX Bluetooth emitter. This garbage device takes an analog audio signal and commands over 5-volt serial. From the start, I wanted to have the ability to control the board from the iPod to set up what device it should connect to, and at the time, I thought the only way to do this was over I2C because I wasn't sure how to use serial from the Rockbox bootloader. So I wrote code for a PIC that acted as an I2C to serial bridge. You can find that code in my GitHub if it's at all useful to you. However, there were some pretty obvious issues with the design. Okay, so I was able to get it to pair to the Google Home Mini here. It wouldn't work with either of these Bluetooth speakers for some reason. It's real picky. But that's coming from the iPod. It sounds terrible. There's ground loop noise. I need to isolate it somehow. I think maybe with a 1-to-1 transformer. But it keeps crashing the Bluetooth module. And I'm just hearing like ground loop noise. So you can hear the absolutely atrocious ground loop noise. It could be coming from anything, honestly. This is just a horrible mess. I never fully tested this board and only assembled it to show you what it would have looked like because it only supported Bluetooth 4.1 and the board wasn't super reliable and the ground loop noise was awful. It also didn't work with all of my speakers or with my will to live, so I went back to the drawing board and decided not to reach for the stars, but just an inch higher. I considered using an ESP32 because of its Bluetooth support, its I2S support, and its ease of use and availability. It also has a multitude of other features if there's ever a need to expand functionality. Step 1 was, of course, seeing if the iPod used I2S to send audio from the CPU to the DAC. I2S is a data protocol used to transmit audio short distances. It consists of 3 signals, the data, the clock, and the word select, so that the data can be split over left and right stereo channels. I was initially worried that it would use another standard called SPDIF, or SPDIF, but I found the I2S lines on the iPod logic board here. I also found the main I2C bus for intercepting volume commands because the audio data is always sent at full volume to the DAC, and the volume is set using an I2C command. Now I needed a physical proof of concept. I looked for other places to pull the signals off the board, but I could only find them readily accessible at the edge of the DAC chip. So I took it to Appleton, because my soldering isn't that good. I'm here with Wesley, of course. You all remember Wesley, right? He's starting us with a server power supplies.
4 server power supplies, thank you very much.
Just tied together with wire and duct tape and hopes and dreams.
And solder.
Right, yeah, that Wesley. We're currently at an undisclosed location where Wesley will perform the micro-soldering required to get the I2S signals out of the Wolfson DAC that the iPod uses. Are you up to the task?
I suppose.
To say this is a tricky solder job is an understatement. I'm not good at soldering. Wesley is pretty good, but even he had the occasional issue with trying to deal with these exceptionally small joints. We bonded it up with UV glue to attempt to secure them. We tested it to make sure that it took, and lo and behold, there were the I2S signals. Let's ignore the one that didn't make it through the surgery. It was now time to validate my design. I had to level shift both I2C and I2S, as well as program the ESP32 to transmit audio over Bluetooth using A2DP. I built a test rig using the components I was going to build my board around, and through some trials and tribulations, I actually got it to work. I was occasionally having issues where the iPod wouldn't boot, but disconnecting the I2C lines seemed to fix it. I figured I2C didn't appreciate the long wire runs, so I decided to go ahead with a PCB design. Some power regulation, protection, and ambitious footprints later, I had my design. Wesley was ridiculously helpful in helping design this board. It turns out when you're dealing with components the size of dust particles, you need to think about how the surface tension of the solder can pull things askew. I got the boards printed, stencils made, and parts ordered, and they arrived a few weeks later. So as previous videos and also earlier segments of this video might suggest, I'm god-awful at soldering, and this involves O201 capacitors and resistors and other passives. So I'm going to try something different. I'm going to try to use sand to reflow solder the iPod boards. I don't have any sand though, so I have to go steal some. It's winter, they won't be missing it. So I'm just going to cook off a lot of the moisture that came with the snow that happened the other night. I used the boards to hold the boards in place under the stencil, set it down, and smeared solder paste across it with an old hotel room key. It took a while, but I got what looked like an even coating. Then I carefully placed the components according to my layout and schematic. The worst one was the bidirectional I2C level shifter because it was really, really small. Finally, I placed it on the sand and cooked it until all of the solder melted. I turned it off and let it cool, and there we have it. A fully functional board, kind of. Besides the occasional bridging such an imperfect process can produce, I ended up with a few problems on this board. First, this transistor that I thought could be used to do the automatic programming, it was silly of me to think I understand how transistors worked. It just shorted the board, so I cut that trace. I also had an esoteric problem where the pull-up resistor for the I2C bus was putting the ESP32 in a weird boot state because I had it attached to a bootstrapping pin. Also, this ambitiously small footprint was a problem because it wouldn't consistently reflow correctly. Also, the voltage drop across this protection diode is undervolted the whole thing, so I worked on another revision of this board to address the issues. I used a bigger I2C shifter, a better diode, and some other improvements. These boards came, I made them, and tested them. However, I was still having a lot of issues with I2C. After looking through the Rockbox bootloader code a little more and playing around with it and adding some stuff to the serial driver, I realized that I could do all the pre-boot communication over serial, and that would also allow the Bluetooth board to send commands back to the iPod over the iPod accessory protocol so I could control it, like play, pause, next, previous, etc. I was still stubborn on trying to make I2C snooping work because I still needed to intercept the volume messages on the bus, because the iPod sends the data to the DAC at full volume, as I said before, and the volume is set using I2C registers, so I needed to pick up on those lines. A lot of thought and design went into this, but it turns out that the iPod's I2C lines are just so sensitive that it might just refuse to boot or freeze at any given time because of a slight disturbance on the I2C line. So I scrapped the entire I2C part of the project, and honestly, I don't miss it. Version 4 of the board was born, a much simpler design and much prettier too. I could have used serial for everything, all along. I also went back to Appleton for more iPods at some point because, and I cannot stress this enough, these things are fragile. Next, I entered a very bad place. Integration hell. I spent a lot of time trying to get the bits of software to work together. I first worked on the ESP32 board software using some excellent A2DP audio libraries. It took me about a month to make it compatible with the media buttons on speakers because it seems like nobody else in the world is trying to use the ESP32 as a transmitter that listens to AVRCP events. If you don't add a 10 millisecond delay, the thing that tells it that it's capable of receiving any notifications whatsoever, it just gets set to 0. I was also having some weird playback issues. This version of the board seems to work with some audio artifacting, so that's pretty cool, I guess. And then I started writing the iPod side of the software, and it wasn't having a very good time either. I honestly don't know what's going on in this video clip, and I don't remember fixing this problem. It sort of just fixed itself, so it might have been a loose connection? I refined both sides of the software to a point of good enough, and finally, it worked. The board, the connections, the interactions with the software, all verified. So I went back to Appleton one last time to get the final iPod soldered, but this time we did the whole thing. We soldered the wires on the DAC and the 30-pin connector and applied the epoxy and attached everything to the Bluetooth board. I brought the iPods back home and began the final integration step, attaching the board to the iPod's battery and installing the software. Unfortunately, only one of the 3 iPods made it back, which is strange because we epoxied the joints, so I was very careful not to destroy the one that was remaining. I tried to use a dark blue faceplate to really put the blue in Bluetooth, but unfortunately I couldn't adhere the click wheel to the faceplate correctly. I put it in a stock light blue faceplate, but this is only where the problems began. The first problem was that the battery was incredibly weak. I figured battery draining would be a problem, but on these older devices with these older batteries, it's hard to even get them to start without a little bit of extra juice in the battery, so I soldered some external power cables, which are critical for testing and programming. I synced music to the iPod and programmed my code onto it. The next problem I had was with programming the Bluetooth board. I rigged it up so I could program it through the 30-pin connector using a breakout board and some unused pins to reset the board. But something weird was going on. I'm not sure if the chip was browning out or if the iPod was holding the required serial lines high. I turned the serial off on the iPod using an emergency feature in my iPod code to allow for programming it in circuit, and that seemed to work. And here, I'll disconnect this. Completely wireless transmission. Bluetooth speaker. Pause. Oh no, connect to power. I'm sorry, don't die, don't. Ah, damn it. Nothing. I got it working for about 30 glorious seconds, and then it stopped. And so did my heart. This was my one iPod, and it broke despite me being so very careful with it. I felt how strange Parts looks 3/4 of the way through his project videos because his iPhone won't turn on. Heartbroken in front of a camera. I did some investigation and discovered that the epoxy I used sucks. This was fast curing epoxy that clearly didn't mix correctly despite using the swirly mixy tip. I thought about how I could fix this and came up with a solution. I could reflow the solder inside the epoxy. To do this, I just touched my iron to the wires and hoped that there was enough solder in the epoxy to remake the connection. It took some time, but I finally got it. The full working proof of concept. Okay, it's completely wireless except for these power cables which go to my thing over here. I'm going to disable it. There, it's off. With the red light. All intents and purposes, it's wireless. The battery's almost dead, so I'm going to go ahead and... I'm afraid to touch it, as I said, so I'm going to turn the power back on. But again, let's this is also completely wireless. So from all the way over here, play pause. Next. Next. Look at that! And previous. Hard to tell. I think it restarted it. Yeah, it did. Yeah, there it goes. Okay. That's awesome. You can hear that it's a little crackly. I assume that's because the signals are rather noisy. But yeah, I'll pause it. But that's so cool. That's repeatable proof of concept. Just don't use crappy epoxy. That's, I guess, the moral of the story. So in terms of range, we can talk about range. I got some Rosenstock playing on here. I'm just going to start backing away from this thing, right? So we're about to hear. The commands still work. I can go next. And I'm controlling an iPod way in the other room over there. And also filling with one hand. This is really hard. But if I step back any further, it starts to get a little glitchy. Commands still work. That's the end of my tape measure. So a little more than 25 feet. And that's how I made the iPod Nano Bluetooth mod. I cherry-picked the interesting parts, but it took a long time, and there was a lot of headbanging and swearing and disappointment that I just decided to leave out. And now you might be wondering, how can I do this myself? It's exceptionally tricky, but clearly not impossible. Here's how you can do it. First, get an iPod Nano, the board, a stencil, all the parts, solder paste, sand, wire, and a lot of patience and flux. Assemble the Bluetooth board, reflowing it using the sand. Go ahead and take apart the iPod, solder the required wires, and secure them down using good epoxy. Attaching to the Bluetooth board, compile and build the software for both the Bluetooth board and the iPod. Flash the iPod and the Bluetooth board, and very gently, if you can, reassemble the iPod. If you want to put the back plate back on, you need to cut a section of it out so the Bluetooth signal can come out of it, or 3D print a slightly thicker body. And that's basically it. More detailed instructions and all of the resources you need to do this are on my GitHub page, linked in the description. I wouldn't do this to an iPod you love. I'd do this to an iPod you're willing to break. I am calling this project finished. Finally, I've prevented myself from starting new projects until I finish this one. I want to get back to the iPod NAND project. It's been a while and I kind of miss it. I also have a stack of 18 iPads just chilling in the corner of my room. What could those be for? And I'm planning something cool that has to do with Crocs, so be sure to get subscribed for all of that. That said, I do have some ideas for future improvements to this project. I'll leave them as an exercise for the bravest among you, but here are some ideas. The ESP32 is a great chip, but the module is huge and power hungry. Maybe we could just use a bare ESP32 chip? Maybe we could use a Nordic semiconductor chip like all the cool kids do. Or, and maybe someday I'll come back to this one, AirTags can theoretically be used as the Bluetooth board with the right connections and software. Feel free to go for it. I accept pull requests and issues in the repository, but for me, I'm moving on. I cannot wait to finally get to these other projects. And I'm so glad that after a year and a half of working, I finally got it. It's finally done.